Hello, welcome back to Mr. Miles Maths. This is going to be our second lesson on set theory, which is going to involve Venn diagrams, which are popular questions on the exam. You need to understand set theory to do this, so make sure you've looked at the set theory video on notation and symbols if you haven't already, because that will help you with the concepts that come up in this. So the first thing we're going to look at is what a Venn diagram is. And the first thing that we're going to do when we're looking at Venn diagrams is talk about the universal set again. Remember, the universal set is the set that has everything in it that we are allowed. We can't have anything outside of the universal set. It's the kind of outset for the question. So we draw that as a big rectangular box on our set theory, on our Venn diagram even. And we can label it in the top corner, this curly capital epsilon, that represents the universal set. Everything in our question is going to have to go inside this rectangle. So that's what we do when we start the question, or that's what you'll see if you see that in the question that they give you. That's the universal set. Everything should be inside that particular set. Sets, if you remember, are denoted by capital letters. On our Venn diagram, we're going to denote them by ovals. You can see a couple that I've kind of prepared earlier here underneath. But just to show you how that works, I can draw a set with an oval or kind of circular shape, and then I can label it as the set A, for example. I can put a set B in like this, and I can put as many sets into this diagram as I want. You're normally going to get 2 sets, potentially 3 sets. We'll look at some exam questions in the third video and the final video on this at a later date. Sometimes the sets might overlap, so you can kind of move this in. And if you remember from the notation, this means that there would be an intersection, elements that are common to both. So that would be this middle bit. And that's what this lesson is going to be all about. It's going to be about which regions, or how to identify regions on our Venn diagrams, how to draw them to start with. Obviously, we've just done that. How to identify particular sets, including all the notation we use. So membership, intersections, unions, subsets, complements of sets. All those things are going to take place in this video. So I've got a few questions here which I've kind of made earlier. So some diagrams. You might want to pause the video in between each so that you've got an idea of so you're drawing it yourself, or to have a go at the questions before I've done them. So the first set we're going to look at is the most simple ones. We're going to look at where A is on our Venn diagram. The first should be quite quick, and you should be happy with these, but you might want to give yourself time just to draw the individual bits out. These are not the complete list of questions they could ask, but it's a few examples of popular things and how you think about each of these questions. So I'm going to get the highlighter out for this rather than the pen, I think. So on our Venn diagram, if we want to look at a particular set, so for example, the set A, if we look at this top left question up here, so this one, if we want to look at the set A, this should be pretty self-explanatory and an insult to your intelligence, but the set A is everything that is encompassed by that oval that makes up A. Okay, note that includes the middle bit there. That middle bit is also part of B, but because it's inside of A, that's included in the set A. So this is how I would draw the set A on my Venn diagram. It would look like this. Everything inside that oval that encloses A. And in very similar fashion, our set B, we would have everything that is enclosed by B. So this would be our set B, all the stuff that's inside B. Notice we don't have kind of individual elements like we did on the first video here. We're just looking at the particular sets and how they're shown on a Venn diagram. Again, if you want to pause the video in between, have a go first. That would be a good idea. So 2 more sets. Good idea to pause here, get the left one drawn, and then you can have a go at it yourselves. In fact, I'll start labeling them. So we've done 1 and 2. So if we look at question 3, pause the video, draw it out, have a go at what you think that might look like. So the intersection of these sets, this is the N. Remember this big capital N thing in the middle. This is the intersection of the 2 sets. So this is a combination of both sets. Well, what is common to both sets? We've got to be careful with how we say it. So things that are in both sets. So elements or members that are common to both sets. So this intersection is this middle part here, because in that part of the Venn diagram, that part includes the things that are in A, and they are also in B as well. They've got to be in both sets. That's where the sets overlap on the Venn diagram, because the parts of that will be in A and they will be in B as well. Number 4, again, if you want to pause, draw it out, have a little think about the union, that A union B would be on our diagram, if you can remember what union means, and then you can have a go. So A union B, if you pause and come back, A union B means it can be in A, or it can be in B, or it can be in both those sets. So the union is just everything from both sets. So the union, if I was shading in my Venn diagram, I can shade in absolutely everything that's in A or B. So that's the whole of those two kind of oval shapes, everything circled in there. So A union B is A or B or both. That means I take everything from A, so I can shade all of A, take everything from B, I can shade all of B, and within that, the intersection will also have been shaded. Let's have a look at 5. Oh, sorry. Let's have a look at 5. So 5 is A dash. Again, if you want to pause the video, draw it out and have a go at what you think this might be. A dash or A complement is those things that are not in the set A. So not in A, if I was shading this, is everything outside of A. So I'll just go all the way around. It'll take a little bit of time. Try to show artwork. Mine is not very good. So shade everything that is not in A. So I can have all the bits in the universal set that are outside A and B. As long as it's outside of A, I can take it. So this is what A complement would look like. Everything shaded outside A. Okay, notice how the intersection, sorry, I shouldn't really go, well, I shouldn't go out the rectangle. The intersection there is B, but because it's part of A, this bit here, because it's part of A as well, I cannot have that in the complement of A. It's not in A, means I cannot have any part of A, so any bit encircled by A, I'm not allowed to have. And in a similar fashion, if you look at the second one, if you want to pause it, so the second one, this is number 6 now, you can pause it. B complement will be done in a similar fashion, a little bit time consuming, but not in B is everything outside of B. So I can shade all this as it's outside of B and all this. Just be careful going around the outside of B. Again, hopefully you're getting the idea of how these questions work and how all the stuff from the first video, all the elements, membership, what sets are, how all that kind of plays a part within this. So not in B means everything outside of B, and that'll be question 6. Okay, I've got 4 more questions to do, and then we'll look at some more exam style questions where we've actually got the elements in there. So 7 and 8. So this is going to become a little bit more difficult. You have to think about this a little bit more. Again, you may want to pause the video before you answer each question, get it drawn, have a go at shading it yourself with pencil, and then you can come back to my answers afterwards. So A intersection, B complement. So you've got to be a little bit more careful here. We're combining sets. So it's got to be in A and it's got to not be in B. I need to think about the first the initial part of this is, well, it's got to be in A. If it's in the intersection, it has to be in both these things. So the fact that it's got to be in A at the start, so the fact that A is there in the intersection, means it has to be inside A. So I'm already narrowing down. So if you consider one of the sets at a time, consider the first one A, that's going to narrow it down because it's got to be in there to be in the intersection. So it's got to be in A, so that means I'm considering just this part to start with. So that would be in A, so it's got to be in there if it's going to be in any intersection involving A. But also, it's got to not be in B. So it needs to be in A, so inside A, but not in B means I cannot have the intersection of the two sets. So A and not B, or A and B complement, would be just this bit, which would not include the intersection because it can't be in B and to be into this intersection. So these ones make you think a little bit more. 8, again, if you want to pause and have a go, draw it out, then please do. So question 8 is a union. And union's a little bit more interesting. This one's always more confusing for people. But remember, union can be in one or the other or both. And it's the or the other bit which is important. So if it's not in A, because it's the union, I can take anything not in A. So I can shade everything not in A to start with, just like we did with A complement, because the union takes everything from both sets. So if it's not in A, it's going to be in the union. So all this can be shaded as it's not in A. Okay, and this time I can actually leave that shading in because the union draws from both those sets. So this must be correct. So that's not A, So that must be in the union of not A. But I'm union with B here, so I can have anything that's in B as well. Well, I've already got part of B shaded, this part, because that's part of not A. So that can just stay shaded. I'm happy with that. Or it can't if I accidentally rub it out. There we go. But because I can also have anything else in B, I can include anything that's in B. And that actually includes this part of the diagram in the middle here, the intersection. So this would be not A or B. So the important part here is not A means I shade everything outside A. But or B means I shade anything that B has. And because it's a union, I can have the bit that looks like it shouldn't be there. That bit that's in A, you feel like, oh, that shouldn't be there because of A complement. But because it's in B, we're allowed to take it within the union. You may want to have a little think about that. That's always tends to be confusing. Okay, and then last couple we're going to look at 9 and 10 in this part, and then we'll move on. So 9 and 10, we're going to have a look at, sorry, I should scroll down a little bit further. So A union B complement. So the best way of thinking about these ones that are bracketed and have complements is to think about A union B, so what that is, and then the complement just means anything not in that. Again, if you want to pause and have a go, please do. So A union B, if you remember A union B, that's everything kind of inside. I won't fully shade it perfectly, but everything inside all of there. So A union B complement means not in that part. So that means we can take anything that's not in the union of the two sets. So that means I can take everything around the outside. So I will shade that. And this is getting a bit trickier. This is kind of like your tougher questions on your GCSE. Looking at maybe grade 7 upwards from here for these kind of questions where you just got to think a little bit more and be very logical and break it down to two different sets that you've got, and then obviously your complement as well. Please note this bit should not be shaded. That's just like my poor artwork, like I said. So A union B complement means A or B, but they're not in that part, so not in A or B. And then the last little one I'm going to look at before I look at some kind of more questions with actual values in is a subset. So if you remember this notation, this kind of C, B is contained in A, I teach it and remember it as how I would draw it in a Venn diagram. If you want to pause and have a go, please do. So a subset is a smaller part of a bigger set, if you remember. So if my A would be a bigger set here because B is a subset of A, then B would be entirely enclosed by A. So all of B is in A, but A might have some additional bits and bobs as well. So there's some examples of shading on Venn diagrams, which they might well ask you to do, and how maybe a subset looks or how a complement might look. Now we're going to go into some actual questions on Venn diagrams and with actual elements inside them. Again, you might have to pause at the start so you can think about it, but I'm going to draw these out for you now. Okay, so example 1. And make sure you're writing this down and you're keeping up. Oops, did not want an arrow on that. Sorry. But I did want it to be straight. Okay, so example 1. So I'm going to define this as the universal set to start with. I'm going to give you this. So the universal set, I'm going to make 1 to 10. So there's my universal set. So I'll say if this is true, and I'm going to make A equal to 1, 3, 4, 7, and 8. I'm going to make B equal to 2, 4, and 7. Okay, and we're going to represent this on a Venn diagram. If you're feeling bold, have a pause, have a go, and you can come back to it. So the first thing to do, universal set, we're going to need a big rectangle in order to define our universal set and have our capital epsilon, this big curly E. So I've got two different sets here. So we're going to draw these sets, and it's always a good idea to use pencil for diagrams in case you get it wrong. You only get one area to do this in your exam, and you want to make sure you get it right, so you don't have to request additional paper. So A was 1, 3, 4, 7, 8. B is 2, 4, and 7. So we hopefully can see that we can put our A in. And we could put A in kind of without thinking about anything else. Our members of A or our elements of A are 1, 3, 4, 7, 8. So they can just go in there if we want. But if you look at B as well, B has 2, 4 and 7 in it. And you can see, hopefully, between these two sets, there's 4 and 7 in both. There is overlap. So these sets do intersect. They have an intersection, so they will overlap on our Venn diagram. So if I think a little bit ahead, then I can make sure when I do this, I draw my B. And it doesn't matter how big these shapes are. In fact, I will just do this to make it a bit easier. Paste. Still getting better with the tech. So we'd have it like this. Work in progress. So we'd have A and B like this. So there would be an overlap because of that commonality, those common elements in the intersection. So they are going to go in here. 4 and 7 are going to go in here. So that's where they lie, because they're in both sets. There they are. There they are. But the element 2 is only in B. Here. So that's going to sit by itself in this part. It's in B, but not in A. So it's going to go there. And then A has got some other elements, so the 1, the 3, and the 8, which are not in B, so they're going to sit just in that part of A. And then I need to make sure I finish everything off. Oops, sorry, I'm not careful enough. Put my 3 back in. You remember the universal set is everything in the question, so I need to fill in all the bits that aren't in A or B outside of A and B. So I've got 1, 2, 3, and 4 covered, so 5 will sit somewhere on the outside. 6 will sit somewhere on the outside, 7 and 8 are in there, and then 9 and 10 will sit somewhere on the outside. It doesn't matter where you put them, but as long as they're outside of A and B, because they're not in the set A or in the set B. So this is how I would look at this on a Venn diagram. And then from here, we're going to have a little look at the number of elements in particular sets. So if I asked you the number of elements, so part 1, part A, I'll call it. So if I went like this, if you remember rightly from our notation that from the other video, this means the number of things in A, the number of elements in A. So if I look at A is everything that is highlighted here. So all I do is I count up the number of things that are in that shaded bit I've got. And there are 5 different elements in there. There's the 1, the 3, the 4, the 7, and the 8. So the number in A would be 5. Let's pick a different thing. So a number in B, again, if you want to pause each stage and have a go, please do. So the number in B, how many elements are in B? So this is this part, and there are 3 different elements in there. So this is just 3. And remember, this is the number of things. I don't need my curly brackets because I'm not defining a set. I'm just talking about the number of things in that particular set. Okay, C. Now let's have a look at A complement. So a number of things in A complement. Pause if you want, have a go. So things not in A, there is the 6, the 9, the 2, the 10, and the 5. So this should be 5. So this includes this. This is not in A, not in A, not in A, not in A, not in A. The 4 and the 7, although they're in B, they are also in A because they are encompassed by that oval shape that represents A. So I cannot take them for not A. And then the next one, we'll have a look at not in, no, in fact, we'll go for number in A intersection B. Again, if you want to pause and have a go, please do. So how many elements are in the intersection of A and B? So here's the intersection. 2 things in there. And then the union, A union B. Again, if you want to pause, have a go. So A union B is A or B. So that means I can take anything in A or B or both. I don't take things twice if they are in the intersection. I only take them once. So this is A union B. So the number of things in there, there's the 1, the 2, the 3, the 4, the 7, and the 8. Still counting on my fingers. So there are 6 elements in total in A union B. And then we'll go for one more for this particular question. How about the number in A complement intersection B? Sorry, it's not very neat. So A complement intersection B. So if you want to pause and have a go, please do. So not in A, and it's got to be in B. So not in A means I'm only considering things outside of A. And this is the intersection, so it has to be common. So this means it cannot be in A. full stop. So I can't consider any of A at all. But then the intersection with B means it has to be in B. So that narrows it down a little bit further. So anything not in B I can remove, which is these. Oops, sorry, at the top of the 5. So that just leaves me with 2. So it's just one element in not in A and in B. A complement intersection B. So that's example 1, just an example of numbers of elements and building up a Venn diagram question when we've got actual values and actual members. So a couple more questions to look at and then we are done. So we'll go example 2. Remember, you can pause at any time, play catch up. That's a good idea. So example 2, so again, I'm going to define the universal set to start with. That's not very good, epsilon. So if we define this to start, so we'll go 1 to 12, 6, 7, 8, 9, 10, 11, and 12. So there's my universal set for this particular question. And then I'm going to say, and we'll make A equal to the odd numbers. If you want to write them out separately, that's fine. I'll do that in a second. I'm going to make B equal to 1, 3, 9, and 11. And notice how I'm defining sets here. So capital letters, equal signs, and I've got the curly brackets because these are the actual sets, not the number. See, all the little ends mean the number of things in that set. This is the actual set and what's in it. And C, I'm going to make 2 and 8. And if you thought about what A might be here, then A, the odd numbers is actually 1, 3, 5, 7, 9, and 11. And remember, 13, 15, 17, yes, they're odd numbers, but because they're not in the universal set, they can't take part in this question. Okay, so we're going to draw this on a Venn diagram with the individual values. I'm going to talk a little bit about this question overall. So, represent on a Venn diagram. Again, if I'm a bit quick, just pause and you can catch up with the writing and the drawing or have a go at the question yourself. So a big rectangular box for the universal set, and we'll write that in the top corner. So A, B, and C. So let's have a little think. So A is all the odd numbers. So A is going to be quite a big set. It's quite a lot to fit in there. It's got the most numbers in it out of all of them. So I'll make it nice and big. B has got 1, 3, 9, and 11. So if we think about the link between this and A, 1, 3, 9, 11, they're all in A. So B is actually a smaller part of A. So we could actually write that B is a subset of A here. It's not letting me rub these out. There we go. And in terms of my Venn diagram, that means B is going to lie entirely within A. Because it's a smaller version. All those things that are in B are in A as well. A's just got some additional bits to it. So we can put 1, 3, 9, and 11 in here. And also that means in A we can put the other two odd numbers, which are 5 and 7. So they're my odd numbers, all inside A, which is the odd numbers. But B is only 4 of those odd numbers. So it goes inside, it's a subset. We could write B is a subset of A if we wanted to. It's a smaller part. C is 2 and 8. They're both even numbers. So C, I'm going to draw outside everything. There'll be no overlap. And C will just have 2 and 8 sitting inside it. And then we need to make sure we include everything else in the universal set, which we haven't included. So 1, 2, 3 are done, but 4 is not in any of those sets, so it's going to sit outside. 5 is there, 6 is not, 7, 8, 9, and then 10 is not taken into account, so 10 is going to sit on the outside. Oh, and there's 12 as well. So I think ascending order, just arrange it systematically, it's much easier to kind of come to terms with. And then I'll have some other little questions on this. Again, you might want to pause in between. We'll look at the number in A intersection B. If you want to pause, then please do. Have a go. So A intersection B means it's got to be in A, so that narrows it down already to everything inside A, so I can discard things not in A, so it's this bit. Or if I want to make it a little bit nicer for you to look at, probably, that's all these. But then the intersection means it has to be common to B as well. So the things that are not in B, i.e. the 5 and the 7, I can discard them because it needs to be in both. So there's 1, 3, 9, 11 is the set, A intersection B, and there are 4 things. Okay, if I wanted to write the full actual set, it would be this. And we can see from the diagram that that has 4 members in it as well. So it all kind of ties together, it has to make sense. Let's have a look at the number in A intersection C. So this means it has to be in A, and it has to be in C. So I'm taking them out as I go. There we go. So it's got to be in A, and it's got to be in C. So it has to be in A, which has to be in here. But then it has to be in C as well. And because it's the intersection, it's got to be common to both those sets. There's no overlap. There's no common elements here. So this means this is 0. And if you remember, if I wanted to write this properly, not like that, scribbly. If I wanted to write this properly, it's not like in my pen, sorry. Then A intersection C would be equal to this little symbol, which means the empty set. There's no overlap, there's nothing common, there's no elements in that set, but you could still be asked it. How about the number in B union C? Pause, have a think about B union C. So B union C means B or C. B or C is everything in B. So there's 4 things there, or I can take it in C, or both, but there's no overlap. So there's actually going to be 6 different things in there. And again, if I want to look at the full set in all its glory, B union C would be 1, 2, 3, 8, 9, and 11. So there'd be 6 things in that set, all highlighted there. So B union C means it can be in B, so take all of B, or it can be C, take all of C, or both. If there's any overlap, you just take it the once. Bit different from the intersection, which narrows things down further and further and further. Okay, and there's some more examples of a number of things in different kind of sets. And then the last bit we will do, I think, is when they actually define the number of elements in a set. You can make up quite different questions on this as well, but hopefully this has given you a good idea. And we will do some exam style ones as well, where we look at actual exam questions in the next video. Okay, so example 3, we're going to just give you a slightly different information in this. So I'm going to say if the number of elements in the universal set is 35, I'm going to give you the number in A intersection B, which is 7, the number in A, which is 12, and the number in B, which is 21. Okay, then represent this on a Venn diagram, I should say. This time we're going to show the number. So that's going to be important. So show the number of elements in each set. So rather than on previous examples where we've shown the actual values, every single individual value is taken into account. Here we're just going to look at, sometimes in a Venn diagram, you just write the number of things in a particular part of the Venn diagram. That's what we're going to do here. So slight difference, so you have to read the question very carefully. Quite often they put it in bold, so do look out for it. So normally with these, they might give you this already. So we've got a universal set. We've got a set A, which is going to look like this. We've got a set B, just going to look something like this. Again, don't worry too much about the size. There is overlap because there is intersection here. There are 7 things in that intersection, and that's going to be a good starting point here. So there's 35 things in total. We don't know where those 35 things are allocated. So we know that in total, the 4 different regions we've got here of the Venn diagram must total to 35. But we need a bit more specific information. The number in A is 12, but we don't know how those 12 are split. So this bit and this bit, the total of them must be equal to 12. But we don't know how that's split until we go a little bit further and think about the detail of this. So don't just think, oh, there's 12 in A, I can put 12 in here. Okay, because this bit here, if I label the cross again, this bit is also going to be included in A because it's in the intersection of A and B and it's in that oval shape. So the good part to start with this is the intersection, because we know that's one little bit and there's no other kind of, this area is not split up into different parts. It's just that middle bit. So the number in the middle is 7. Okay, because the intersection is 7. That means the number in A is 12. Well, if there's 7 in the intersection, that means those just in A, there'll be the 12 things that are in all of A minus the bits that are in both. So that'll just leave us with 5 elements. So I should have 5 here, because there's the total of 12 within A, 7 in the middle part in both sets, which means there must be 5 that are just in the set A and not in B. And in similar fashion, the number in B is 21, but we know there are 7 in the intersection. So if we subtract, we'll get 14. So that means there must be 14 in this part of the Venn diagram, because there's 21 in B in total, 7 are in that intersection, which means we're just left over with 14 in the bit that's just B, but not in A. And then finally, we can use the fact about the universal set, which is 35. There's 35 things in total in the question. So if I take away the other bits, the 5, the 7, and the 14, that's minus 26. That tells us there will be 9 things on the outside. And notice how these represent the number of things, not the actual individual elements, the number of values that are in each part of the set. And then from here, they can ask lots and lots of different questions. So we'll go through 5 different questions and then we are done. So we're going to have question A is find. So all these are going to be find. So we're going to look at the number of elements in A complement. Again, if you want to pause the video and have a go, please do. So not in A is this and this. So not in A, there will be 23 things. We'll have a look at the number in A union B. Again, if you want to pause the video and have a go, please do. So A union B means A or B or both. So we can have A, which is these two, or we can have B. So we take the 14. We don't need to take the 7 again because it's already included, or both. That's the 7 included. So we'll have the 5. Oops, sorry. We're going to have 5 here. We're going to have 7, and we're going to have 14, which is 26 in those parts. Part C, how about the number in A and not B? So A intersection, not B. Again, I'll remove the highlighter. If you want to pause the video, have a go, then please do. So this is the intersection, remember? So it's got to be common to both. So narrow it down straight away. So this means we can go into A, must be an A, so it's got to be 5 and the 7, or the 12 in total. But not B means I will have to remove anything that is in B, which removes that 7. So this would just be 5. And then last 2 bits, we'll go for the number in, this time we'll go for a double bracket, just to make it a bit trickier. So this is the number in A and B complement. Again, if you want to pause the video and have a go, please do. So A intersection B is the middle part, which is the 7. So I'd go straight into the middle of this, always go brackets, always go into the most inner part of the question. So A intersection B is that. But then we want the complement of that. So we want not that 7, which means we are left with the 5, the 14, and the 9. So 5, 9, and 14. So there are 28 things in that set. And the last one, I remove markings, but not the numbers, hopefully. And then this is the number in A or not B. If you want to pause and have a go, please do. This is probably the hardest one to finish on. So pause, have a go. So A or not B. This is confusing for people because it's a union. And union means I can have A or not B in this case, or I can have both those things. So the best way of doing this is to think about, well, I can take anything from A. So that's the 5 and the 7. Don't worry about the fact that, oh, there's not B, I'm not allowed to have B, I can't have the 7. Forget the not B for now. You're focusing on a union, and then if I can draw anything from the first set, so I can draw anything from A, that will include the 7. So that is going to be part of this. And then I can add in anything from not B. So not B, well, I've got the 5 already. And the other thing that's not B is the 9. So I can take the 9 as well. So that would be or not B. And that will include everything in the union. And then, oops. So let me remove them. I need to get better at erasing without taking out the question. So A or not B or both those things. So this includes the 5, the 7 and the 9. So it's take anything from A, the 5 and the 7, forget the not B because it's a union. Intersection is different, that narrows it down. But take anything from A or not B. Not B means the 5 or the 9. 7's already there, so 5, 7 and 9. So that'll be 21. And that takes us to the end of this lesson. And again, a little bit longer than I thought it was going to be this video, but hopefully that's helped you with some Venn diagrams. The third and final video, we will look at a load of exam style questions. But nice to see you all. Thank you for watching. I hope you've managed to keep up with everything. Remember, if it's a little bit quick or there's things that you're not sure about, I'm saying that very quickly in saying it, then please do pause and then you can write things down and have a little think and make sure you've got things written down at the same time. Hopefully this is useful and hopefully I'll join you in the next video. Thank you. See you.